那我要做一个推荐，所以可能我们要早一点准备好 PPT。
哦，好，谢谢，麻烦您了。
我们几轮那个呢？
好的呀，前一次的修改我可以更新一下。
哎，对，就那个框架就行。我看了以后，我再找这个几个比较资深的，我们再沟通一下，听听他们的意见。最终反正我代表我们26个院士联名。后来有些院士没有这个，因为没有空间了，当时也没有写进去，还有意见说这个，哎，我原来答应过，后来没找。比如说像复旦大学金雅秋院士就说，哎，这个黄校长你怎么没找我签字啊？我说后来没地方签了。没有化学背景的，除了我是这个混进去的，然后其他的他都是偏这个是吧？物理啊、数学啊、计算机啊，这个电子科学技术。然后这个化学，他说，哎，怎么报我们学部呢？这个不对啊，应该到化学部。这个技术差错，没事。好事多磨，好事多磨。这个
辛苦。
所以这次非常感谢，非常感谢。哎，
没有，很高兴有这个机会一起，也是可以联络。
是。所以这个您和永刚这个院士都做得非常出色，所以这个我们编辑部商量最有代表性，所以这个请你们2位做报告。然后国内这边呢，这个正好这个陈永华教授在钙钛矿方面今年也有一些不错的工作，包括在 Science 啊、Nature Energy、Nature Electronics、Nature Com 发了几篇，我说也给年轻一点的同志有机会。他是青年千人，从这个美国回来的，从这个 Case West Reserve 啊，从那儿回来啊。这个
发展很快。
哎，做的也不错。明年希望能够这个也是能够有一些这个新的支持嘛。马上就开始了。时间这个好。
永刚你好。
哎，陈南好。
你好。
哎，永刚兄，好久不见啊！好久不见。
黄伟好，好久不见了，真是
非常感谢啊。
谢谢。
状态不错，跟几年前没有什么区别。
没有。
最近偷偷的去这个听了你老兄好几个报告。
真的，我就讲了一个，我记得好像。
你前几天那个80级的那个报告做得非常好。对吧？
谢谢。
哎，这个
不，今天也完全是不同的 topic， 今天完全不同的 topic。
哎，那个角度也非常好，我觉得讲的这个非常好。
谢谢。
我全程听的。
谢谢，不敢当，谢谢啊！你大忙人还全程的，实在不敢当。
对，非常好。这个美国那边疫情怎么样啊？现在控制了？
哲丹，你们那边怎么样啊？
我们这边好像还好，不觉得什么，反正就是比较大家都注意一些。那个在办公室啊，或者在房间里面，总是还是戴着那个口罩，出去就还可以。但是吃饭呢，做其他事也都正常，就是一直戴着口罩在外面。对，你们呢？
我们这也一样，就是在学校里你要求都戴口罩了，我们在学校里都要求戴口罩。
是，我们也是呀，对。所以现在很多会议又变成本来是准备要人去的，现在很多会议又变成又是网上的了。因为现在出差很少，很久没出差了。
是吧？我也是。我已经是18个月没出差了。
是啊，
都差不多。
对啊，就封了之后，去年3月就度过一次假，飞了一次飞机，那个其他就再也没飞过了。
简谱是不是我们差不多了？
好，这边网络可以啊，听得见吗？那我们就开始好吗
？It's about time. Shall we start?
好的，尊敬的
distinguished guests, including academicians, Good morning. Today we are gathered here for Research Editor-in-Chief Ge Zhi International Forum. We are convened to celebrate the 3rd anniversary of the research journal, and this is organized by Science and Technology Review. It's a non-profit. It's a premium event designed to encourage convergence of different disciplines to facilitate cross-border collaboration. And we have successfully held these sessions for 3 times. For the first time, we had a dialogue on COVID-19. For the 2nd anniversary, we looked into frontier technologies of lithium batteries. And also, we had a special session on the latest developments on highlight and hotspot materials. Today, we're gathered here to explore flexible electronics today and the future. We are quite honored to have not only multiple professors, Editor-in-Chief Huang Wei, but also Bill Moran and Cui Tianhong. We have Chen Yonghua, professor from Nanjing University of Technology. We have Bao Zhenan, professor of Stanford University, and Professor Wang Yonggang from Northwestern University. Both of them are academicians of various science institutes. Now I'd like to give the floor to Huang Wei, the Editor-in-Chief of Research. Distinguished guests, academician Huang and Bao. Dear colleagues and scientists, good morning and good evening if you are in the United States. It is such a pleasure to meet all of you in the beautiful autumn, and we're gathered here to celebrate the 3rd anniversary of Research Journal. On behalf of the Editor Committee, I'd like to extend the warmest welcome and gratitude to all of you and to those who have pledged their strong support to Research Journal. Special thanks to academician Bao and Huang for receiving our invitation. I'd like to also thank my colleague Cui Tianhong for the hard work in the past 3 years. If we look around the world, the Industrial Revolution is brewing and happening everywhere, including flexible electronics. They have led cluster technological breakthroughs and have driven new changes. They are going to be pioneering and pace-setting new developments, and this would be a major pathway where China contributes its own wisdom and technologies on flexible electronics, artificial intelligence, space science, life science, energy science, data science, among altogether 8 frontier and technology areas. We have identified them as the most promising areas to see new breakthroughs. And we used the first letters of the 8 areas in English. It's famished, which means extremely hungry. We refer to these 8 areas as hungry science, and these are the areas where we're most desperate for latest development. We want to make sure that we are preemptive. We are able to build and hold these core technologies and build fundamental science expertise so that we can explore their potential from the economic side as well. Since last century, US has already initiated its innovative education program. I believe my colleagues here, including the academicians, know this very well. And in 1986, National Science Bond has advocated for greater attention for science education. And then President Bush has called for the new initiative, and also Barack Obama followed on further expanding that science education. And when dealing with such frontier technologies, we need to fully recognize the shortage of core technologies and strengthen science and technological innovation. We need to strengthen mathematics, life science, and basic science represented by material science. And all of these key areas are combined into NILDA that represents fundamental. And innovation very often emerge from cross-disciplinary endeavors, and multidisciplinary effort is already the trend of the time, and is also how breakthroughs are made. So we will try to boost NILTA as a way to encourage more disciplines to break their boundaries, to explore possibilities of cross-disciplinary efforts, so that they will be able to boost their capacity in generating new knowledge. And the science and technology is a representation of how competitive a country is, and outstanding science journal will play a very important role to a country, particularly as China now seeks to build a strong science base. And we will not only help to transfer knowledge to application, but also contribute to national soft power. Nature and science have been leading multiple areas of research, and they also played a crucial role in leading the dialogue in new technologies, and they have created a major platform for innovation. We have 3 speakers, particularly academician Bao and Huang have published heavily on nature and science, and their works have been keenly followed by international colleagues. And in recent years, China has already been contributing more and more to scientific journals, making China one of the largest producer of this kind. Already 418,000 articles come from China. Many of them are of a high quality, but China still do not have an influential science journal that can be comparable to science and nature. So in the effort to strengthen our voice of science community, it's quite urgent to build our own science journal. And we have given this context, built the Science and Technology Review as a way to expand the partnership. And research is the only partner journal that science has entered into collaboration with. It aims to explore our core strengths, and is also a major milestone in China's research and development. Thanks to this high impact platform, research were able to quickly circulate among the science community. It has been recognized by CX, GMC COS, and altogether 9 database. And based on set score 2020 ranking, out of 110 comprehensive journals, research ranked number 11. It's among the top 10%. It's also one of the top 3 in China. I believe this momentum will continue to expand. Research has just convened its second committee. We have 136 international experts with 33 academicians from both China and beyond. We have a 3-step strategy that will push us towards a comparable international scientific journal of international influence in the next 3 to 5 years. According to our plan, in the next 3 years, we will facilitate academic exchanges, better serve scientists, and pave the way for building our own strengths in science and research. Centering around China's mainstream, we would like to build different journal clusters, to build think tanks, and provide policy support for major decisions. To celebrate the 3rd anniversary of research, we are convened here for the 3rd anniversary academic report theming on flexible electronics. This is also a keenly followed area. I'd like to thank the 2 academicians and Professor Chen for bringing us your fascinating work. I would hope this could be an opportunity for channeling resources and building the dialogue so that we can expand exchanges in frontier technologies. And this is an effort to give full play to research as a platform for international dialogue. Let's join hands in better understanding the frontier changes to facilitate frontier changes so that we can jointly contribute to a brighter future. Lastly, I'd like to count on your continuous support and advocacy for research, and we welcome all of your submissions to research so that we could further contribute to scientific new advancement. Thank you. Lastly, wish a complete success to the forum. Thank you for your warm remarks. I'd like to give the floor to Bill Moran, publisher of Science family of journals.
Good morning, everyone. And thank you for the opportunity to be here today with you and to say congratulations on your 3-year anniversary. It's a very proud moment for all of you. So again, thank you for having me here and congratulations. One of the things I'd like to talk about right now is just to give a little history on AAAS and the American Association for the Advancement of Science. It was back in 1848 we first started the American Association for the Advancement of Science. Then in 1880, it was with Thomas Edison, who gave us some seed money, and we started science. He felt there needed to be, and our board of directors felt there needed to be a better forum for communication of science. And why I'm bringing this up, it's important. I was just listening to some of the words in the beginning and the talk about the future, 3 years, 5 years, becoming an international journal, which you already are, but continuing that. And it's important that we learn from each other. One of the reasons why we started the Science Partner Journals is because we felt it aligned with our mission to work with others, collaborations, cooperation. We believe in science without borders. So for us, it's very important and very important work to make sure that you succeed. Our success is your success. So with that, I really wanted to say thank you for the opportunity to be here on this momentous occasion of your 3-year anniversary. And again, I hope you all have a great forum. Thank you.
Thank you, Bill. 感谢 Bill Moran 的致辞。
Thank you, Bill Moran, for the warm remarks. Now I'd like to give the floor to the International Editor-in-Chief of Research, Cui Tianhong, to give remarks and the update on this.
Introduction. I also appreciate academician Huang's opening remark and overview of the Science Partner Journal issues. I also appreciate Dr. Moran's opening remark. With my position as a co-editor-in-chief, I'd like to appreciate the 3 speakers, Professor Bao, Professor Huang, and Professor Chen. We are looking forward to your wonderful talk. And actually, I personally listened to your talk many times. I really enjoy your wonderful work in the past. I hope that you can support the journal and submit your good work to this new journal research. With this, I'd like to share a few slides about the journal research. I hope it's working now. So this is actually the 3rd year anniversary. We initialized this journal 3 years ago as a multidisciplinary journal with in between China Association of Science and Technology and AAAS in the United States. And actually, the agreement was signed on January 29th, 2018. And then later that year, we published the first paper on August 22nd. Actually, Professor Chen from CNKI University published his first paper. So research is actually run on the science platform. It's the first partner journal from AAAS. And actually, we use all the resources from science and actually publish state-of-the-art journals, state-of-the-art papers from different disciplines. So it's open access journal. So the papers can be accessed globally by so far over 166 countries. So this year, from statistics, we have many views from all over the world. And actually, CAST, China Association of Science and Technology, hold all the copyrights and actually is the owner. And actually, the partner with AAAS try to publish high quality paper in this multidisciplinary journal. As I said, this is actually is a interdisciplinary journal. We publish topics in 11 areas, go all the way from advanced energy, advanced manufacturing, advanced materials, AI, environmental science, flexible electronics, and actually today we have more than three leading experts in the world who are working on flexible electronics who gave us talks. And we also publish topics on health science, information science, micro nanotechnology, quantum information, and space science. So as Academician Huang just mentioned, this journal has been indexed by 9 major databases. I don't want to mention in detail, but actually been indexed by many major index in publication domain. So I'd like to I think as Dr. Moron just mentioned, we have a successful 3-year so far, even though it's still a young journal, but we're making major impact in the interdisciplinary area across the boundaries. And as Dr. Moron also mentioned, science, there is no border. Actually, people has been collaborating, and we have to collaborate. There is no border between countries. So I'd like, before the end of my opening remarks, I'd like to thank all the authors, editors, reviewers, and readers who have been contributing to this journal. We also appreciate the sponsor and owner, China Association of Science and Technology, who financially sponsored this new journal. And also very much appreciate the partner from AAAS and the team from AAAS. They really dedicate to the daily work together with the editorial department of CAST. And actually, we have several magazine editors in Beijing that has been working on this journal on a daily basis. They are really dedicated to work behind the scene. So by the end, I'd like to show the website of this journal and the contact email. If you have some work relevant to this journal, please feel free to contact the editorial office or my co-editor-in-chief, Professor Huang, or myself, and we can have a discussion. You are really welcome to publish your work in this new journal. With this, I'd like to thank all the audience globally and turn it back to Professor Wang, who can continue to run this meeting. Thank you. Thank you all.
谢谢崔教授。
Thank you, Professor Cui. Now we are going to have our academic report. First of all, we have Professor Chen Yonghua from Nanjing University of Technology. He is going to talk about ionic liquid, Perovskite, photovoltaic cell, and Professor Chen, who is elected into the National Top 1000 young talents. He is dedicated to the stability performance research of the perovskite by utilizing ionic liquid in order to solve this issue, and he achieved very amazing progress. Now I'd like to give the floor to Professor Chen to share with us some of the ideas. So the floor is yours, Professor Chen. Thank you, Mr. Wang, for your wonderful introduction. I think that you can see my screen. Yes. And Academician Bao, Academician Huang, Academician Cun, three distinguished guests, ladies and gentlemen, dear students. Good morning. My name is Chen Yonghua. I'm from Advanced Material College, Institute of Advanced Material of Nanjing Technical University. Today, I'm going to talk about perovskite photovoltaic cell. First of all, I want to thank the invitation from the host. I think that I feel very honored to share with you some progress of my research in these 2 years. And this is my presentation agenda. We know that the PV solar energy is greatly needed by the whole world. At present, the PV solar only accounts for 5% of the overall supply. By 2030 or 2050, it will be 13% or 25% respectively. And China, it will be 40%, which means that the overall installed capacity will be greatly enhanced. At present, it is 50 gigawatt. By 2030, it will be 2,480 gigawatt. By 2050, 8,519 gigawatt for the PV solar. And that is dozens of folds of times of growth. The installed capacity by 2030, 270 gigawatt. By 2050, 372 gigawatt. Consequently, the cost of installation and the electricity will be going down, and the average investment will be up, which means more employment opportunities in this sector. We know that the PV solar is our national energy strategy. Its solar battery component is growing year on year because of the double carbon goal set by the government, and with the shipment is 124 gigawatt. PV as known to all, and we have several technologies such as silicon-based PV and film-based PV, and new type of PV technology. And this technology can be used in the rooftop and the road lamp, as well as on the constructions. And another PV material is the perovskite, which is efficient, stable, and low in cost. And this is very high performance semiconductor in comparison to silicon and the other semiconductor in terms of the band gap, absorption coefficient, and the mobility rate, concentration, and the charge carrier. The performance is comparable to the traditional excellent semiconductor material. The band gap is 1.1 to 3.0. Efficiency is up to 10 in the power of 4 to 5. The mobility is up to thousands, hundreds of them. The concentration of the carrier is also very good. Therefore, as a raw material for PV technology, it has a lot of advantage. Especially, perovskite is very abundant. The component cost is very low with very good stability, variable, stretchable, and also it can be easy to process in the solvent, which makes it different from other semiconductors. It has very good strength. Talking about the solvent manufacturing, it uses all kinds of solvent, and perovskite, it has a big problem. It uses a lot of these metal halide and BMF or BMSO, a protic polar solvent, a single type of solvent. And anti-solvent is needed in the glove box, such as the chlorobenzene, toluene, ether. And the performance of this anti-solvent is not very stable. It has to be prepared in the stable environment. A lot of constraints. Therefore, in solvent, people do a lot of work, and this is a inevitable problem you have to solve in the manufacturing, large-scale manufacturing, and GBL plus alcohol, DMSO plus alcohol. And this is not a good solvent. And therefore, we have less toxic, and it is good by using water, but it is not very good in its efficiency. We have done a lot of work, however, and this kind of a solvent system for it is not radically changed. And we will think about the perovskite and its solvent, and what is the chemical interaction between them. Take DMSO, DMF as example. And it is the match between OPB and and this lead halide is structured from C axis, and we stress this structure in order to have a higher solution. And we have two questions. Do other functional groups coordinate with PB2+, so that we can have a higher solvent possibility? And the other, and how about the precursor and the quality of it? We will think about the role played by the halogenated amine and the solvent be regulated, and we invited an ionic liquid that is MAAC in order to construct high-quality perovskite films in air. And MAAC is very simple ionic liquid, and we can have the synthesis and the properties of MAAC ionic liquids. Why we choose MAAC? Because we have the MA root. It has a very good foundation, and it is good for the lead, and also and MA root is very good for preparation. And also we have HAC. It has hydrogen, the bond of hydrogen, and also nitrogen. And you can get a very good system. You can have a very good system of the halogen, and we are able to control and regulate it. However, it has no pungent smell, non-flammable, negligible vapor pressure, stable physical chemical properties. Just like the bean oil or other kind of oil is quite a sticky liquid, it has a very strong performance or property of the ionic liquid. We use MAAC in order to solve. It is a very good solvent, can be easily used to solve these, and it is no color and transparent. It gives you a very good and very enriched chemical property. And first of all, the application of ionic liquid in one-step preparation, we can get very stable performance of perovskite, above 20% efficiency higher. And we think that the ionic liquid can bring in two results. First of all, it's easy in preparation and highly reliable, and we can produce in the air. And also, there is no impact by the humid. And we can give you very good film. And as long as and it is one step, no anti-solvent is needed.
And that really helped to lower the technical threshold for the preparation. You would easily drop the liquid on the membrane, and with a spinning coating, you will be able to have a nice quality of the membrane, no pinhole, and also no need to worry about the flatness of the surface. So you get to see clear strands here. Traditionally, the concentration of lead could be higher than 1 millimole per millimeter, but for this new type of MAAC solvent, the lead concentration is much less. But with this, you would also be able to reduce, not only reduce its impact on the environment, but also reduce its cost of preparation significantly. And the application extension is also built upon its ionized feature. So we start to think about possibility of building an electron transport layer free function here. And traditionally, one would rely on the electron transport layer to realize the high carrier mobility. But because of the stickiness of MAAC, although go after annihilation, some of the ion will flee, but some of them will still remain. Then you will be able to have interfacial dipoles. So instead of reintroduce or prepare interfacial dipoles, you will be able to have in situ construction of individual dipoles that can be then explored to our benefits. And on one hand, we recognize the MAAC high performance, but it's not tolerant. The traditional method was not tolerant of humidity. So we started to think about ways to build efficient and stable, fully inorganic perovskite. And you could see on the left side, traditionally you have the layered structure. But based on the characterization here, with the introduction of MAAC, you will be able to destruct its structure, and by using the hydrogen bond, you will be able to build a powerful structure there. And since it's possible to build in a completely stable device with the introduction of ionized liquid of MAAC in air, we will be able to make a more stable version of perovskite. And we have thought about a third possible application here. And we will be able to use MAAC liquid to improve the quality of thin film. And a key feature is the presence of a larger molecule. By bringing in a sulfur-containing molecule, we will be able to restructure the perovskite structure, and it will help to strengthen the stability of perovskite. So all in all, ion liquid has clear strengths. Of course, conventional solvents are already very good, but with the ion liquid is not toxic, it's stable, you will be able to prepare it in air. You need less lead concentration, which is an extra plus here. And then it's also quite important to understand where did that high efficiency and stability come from in this liquid. Traditionally, to use anti-solvent to prepare a device, we will be able to have a similar efficiency. But if within DMF, non-pacifier was added, no additive was added, then you wouldn't have a fairly high stability. But with MAAC, you don't need any additives to deliver that sound stability. And this result has been published on research already. So we're carefully studying where that stability come from to look into the solvent properties. And you would see lead oxygen bond has been increasing, and and you would have a quite a strong combination that of oxygen and lead that disrupt its original bond. And you would also see the effect of the bonding effect of hydrogen in the bottom that would truly give play to the properties of the solution. And another key feature is limited intermediary phase for MAC perovskite. And with less intermediary phase, you would have less stress, and that will contribute to better stability. And although MAC may flee, but since it's sticky, you would still have a small proportion there maintained within the thin film. And also because it's very small, it wouldn't penetrate perovskite. And with its bond effect, it will be able to have a pacifying effect on the grain boundary and further contribute to the stability of film. And that's also why we're able to have high quality film prepared throughout this process. And that explains the source of stability of the film. And since iron liquid is quite straightforward compound that's easy to prepare, you'd be able to manipulate both sides of these compound. For instance, we have tried with the MA side, and by replacing it with BA. And here you would see traditionally it's usually iodine-based compounds. And we know very well the molecule structure on the left side. But the problem is you don't have a fixed number of layers, and such a structure is usually highly characteristic of multiple quantum wells. But for the butylamine acetate, you will be able to fix the number of layers. Make it 1, make it 4. You don't have the disruption brought by the uncertainty of number of layers. And we were able to prove that structure difference. And you would see from TA here that you have multiple layers. Some are 3, some are 4, some are indefinite. Seen from PL absorption, you would see with more layers. In PL, it's quite clear that it's almost every line indicates a 3-dimensional structure. And that's why you would read from the spectrum that it's a typical feature of 3D structure. And from graph B, you would see instead for BAC, you have a nice single wave, and you would clearly see it's a typical absorption of one layer of the structure. So that gives you a clearly layered structure semiconductor. And seen from crystallinity and also its structure, we will be able to make our comparison here. For BAC, the quantum wells are orderly distributed, and instead, for traditional structure, you would have multiple quantum wells, and because of the lack of orderly display, you wouldn't have a clear readings. Also the stability in air temperature and in the atmosphere would also make this system a highly stable one. Because of the pure phase, and it would be able to carefully wrap perovskite. We also tested under 85 Celsius degree for 600 hours, and also constant light exposure for 1200 hours. Again, the stability was quite satisfactory, with attenuation less than 10%. And because of this attractiveness, we further tried out the methylamine formate possibility, the MAFA. And this is a material that we have identified with the narrowest band gap, and it's also believed to be the most efficient perovskite device. But it has its own problem. It's of alpha phase, known for a poor stability. It will only generate the ideal phase we need at 160 Celsius degree, and also it's quite vulnerable to humidity change. So how can we stabilize perovskite in its alpha phase? So once again, we used MAFA to stabilize in 2 steps. On the right side, on the SAX group, you will see that in DMF solution, you have the dual presence of lead oxygen bond and lead ion bond, and as a result, you have a quite strong coalition of the ion in the solvent. And on the left side, on the contrary, you will be able to have a stabilizing effect delivered by its hydrogen bond, similar to the previous solvent. For instance, here within DMF solvent, after 12 hours, you would gradually see the breakdown of its stability, but in our proposed solvent, it remains to be stable. And in DMF and DMSO, you don't have a clear orientation, and also there are complicated intermediary phase and has to be prepared in a high humidity. So usually you would have to rely on the glove compartment. But for our proposed solvent, you'll be able to prepare it in air environment, and also you will be able to induce oriented growth of the thin film. Then what this feature is going to deliver from top view and the side view, you would see clearly that there are multiple holes present. They are very important. We named it as ion channel because they will be able to see a quite quick move of ion move through these ions and greatly reduce the time needed for reactions between the 2 compounds. And in room temperature, it's quite difficult to deliver alpha phase. Usually, almost exclusively, you would have a delta phase.
Some of them are lead iodine, and it is fully reacted. And in the phase, in the low temperature, we are able to get FAPBL3. It's difficult to realize that in the traditional way of manufacturing. And the other thing, we have a high efficient component in comparison to DMO and DMSO. The efficiency is higher. More importantly, we believe it gives higher stability to the perovskite, 5,000 hours with a little attenuation, heating up in the lab for 500 hours, no problem at all. And the thickness is quite stable, especially in MPV. And 500 hours, the attenuation is only 15%. So the stability is much higher because of in terms of solvent or the crystallization and the nitrogen-hydrogen bond protected by such a bond. Therefore, the stability of the perovskite film is higher. Finally, I want to sum up the development of our work. First of all, we use the ionic liquid as a very special solvent introduced in the component of perovskite. And because it has a lot of properties, and there is chemical interaction, and we can give you higher performance. In 2017, we discovered ionic liquid, and we use it as a solvent to replace DMSO, DFO, and in 2020, step by step, and we realized the preparation of the ionic liquid preparation, and we expand the source of it. In 2021, we have a higher and more new scenario for such a liquid. At the same time, ionic liquid stabilize the perovskite black phase. And this is our design for it. That is the function-oriented optional design, green and non-toxic, stable and high efficient. And that will be the construction of high-quality perovskite PV cell. And I want to say thank you to Academician Huang, Professor Wang, Professor Liu, and Professor Zhang, and my teachers, my students, as well as the support from the fund. And also, I want to thank the research journal, the editorial board for inviting me to make the report on the work we have been doing. Thank you. And also, I'm open for suggestions. And thank you for your wonderful presentation. Do you have any question to ask?
石老师，这个观众中的这个问题会传到
Professor Chen, and probably Mr. Shi, can I see the questions from the audience in the chat box? I have a question from the audience. And the life cycle of the perovskite PV cell at present, and this is the main direction in our research. It is one of the difficulties decided by its actual application. Is it possible to replace the silicon at present? There are some companies who are quite good in it. For example, Professor Huang Zhongwei from Technology University passed the IEC standards. By that standards, 25 years for application. And some other research groups already realize the ongoing sun basing time, and it is a very long duration. Therefore, the stability of the perovskite PV cell is no problem. There is a rumor saying the stability is poor. It's not correct. By my own efforts, no matter its structural or the physical structure, we try to enhance its stability. The stability is high enough. And to us, we believe no problem at all of using perovskite PV cell. Some audience may have the concern. At the present, IEC test is for the silicon battery. Is it applied to perovskite PV? This is for a short-term test. But 20 or 25 years is the same process applied to the perovskite PV cell? This is another very good question. From my perspective, Perovskite is a new type of semiconductor material arousing great attention from the public. Of course, it has its own problem, such as stability. Just now, you talk about IEC standards on silica. This is a very good standard. And some groups and institutions propose that to provide a tailor-made stability test standard for perovskite. I believe very quickly we are going to have such standards for testing. Maybe that standard will be more stringent than the silica, or maybe not so strict. Anyway, it is able to prove perovskite is comparable to the stability of silicon, and another very good progress. Professor Cui, you have one question.
Thank you very much for your publish your original work in research. It's great work. I have a quick question about your testing, the stability testing. So you saw very good stability at room temperature. Did you do elevated temperature testing? For example, test at 60, 65 Celsius. That's actually pretty much the working temperature outside and the sunshine. So did you test, at a little bit higher temperature other than the room temperature?
谢谢崔辩姐，我就用汉语跟您回答吧。
Thank you for your question. I try to answer in Chinese. Well, the stability or under humid environment, yes, we are able to test it. 85 humid and at 85 degrees temperature. And at our lab level, we only have 85 heating as the conditionals, which means we give it package to our perovskite to test the stability. We do not consider the impact of humid. And under 85 degrees, 500 hours, yes, there might be some attenuation. 10 to 20%, that is annual attenuation. Some of the labs are quite good, maybe less 10 or negligible attenuation. And the double 85 standards is the test standards for silica, which is needed for the perovskite. This is a very good question. If it is very well sealed, and we can see negligible influence on the stability. Thank you for the answer. If there is a quick question, due to time constraint, whether perovskite can be used in the integrated circuit. Well, it's highly potential, especially the monocrystal perovskite, because IC needs faster response. Single crystallized perovskite has a high mobility. At present, the manufacturing level for the monocrystal is good enough. If we can use that very well in the perovskite, I believe it has a great potential in using it in the IC, especially in the flexible chip. It will have a higher strength. Thank you very much. Due to time constraint, I want to thank Professor Yonghua. Thank you. Thank you very much. We're going to have Stanford University, Mr. Bao, and who is going to talk about the skin-inspired organic electronics. Probably you know Professor Bao very well. He has published a lot of high-level papers, and Professor Bao is a member of the National Academy of Engineering, member of the American Academy of Arts and Science, and in 2015, and 10 top members were elected, and Professor Bao is one of them. And I'd like to give the floor to Professor Bao. And thank you very much. Thank you, Professor Wang, for your wonderful introduction. I want to say thank you for the invitation. And I want to say thank you to the audience listening to my report. And I want to send my congratulations to the 3rd anniversary of a research journal, 3 years birthday. And I hope this journal could become more prosperous in the future. Now I'd like to set up my screen. In my research group, we have been
working on skin-inspired electronics for the last decade. In this talk, I like to give you some updates on the progress. But before that, I like to first provide some motivations for why organic materials for skin-inspired electronics and some of the developments, the main materials design concepts, and the current status of devices that we can realize, and then end with a summary and the future outlook. So transistors have been the main electronics or the building block for all the modern electronics. It's a simple switch that's used to build electronic circuits and displays. However, today's electronics are all mostly made with silicon, and silicon being a rigid and brittle material. As a result, the electronics made from them are also rigid and brittle. So if we use such electronics to interface with human body, you can see the electronics also tend to be very bulky and difficult to provide intimate contact with human body. Even for implantable devices, very large chunks of batteries and electronics are being implanted. So this can severely limit the potential of electronics. So what we envision is a future where electronics are comfortable, invisible, imperceptible, biocompatible, and also autonomous all at the same time. So skin has been an inspiration for many researchers to develop electronics over many decades, starting from trying to mimic the sensing function of skin for prosthetic hands. And also in the science fictions, the kind of artificial hand that can have enhanced functions have frequently been depicted. And in this field, there have been some really important breakthroughs. One is Takao Sumiya's work, where he showed that organic electronics potentially integrated with sensors could provide the flexibility to mimic the sensing function of human skin. And of course, John Rogers and Yonggang Huang, they pioneered the work of turning rigid electronics into flexible and even stretchable form factor. So in my group, we started our journey in using skin as an inspiration in the 2000s, where we started by first trying to use flexible materials to mimic the sense of touch of skin. But I think the important aspects or the contribution that we made to the field is one, really to realize the skin as an integrated electronic material and a system. So as an electronic material, skin is not only providing the sensing functionality, but also have also not only flexibility, but stretchability, biodegradability, and self-healing, all incorporated into this one single material. But such electronic materials did not exist before. And the other thing that I think that was important that we realized was that skin also as an electronic system, it basically had the sensing and signal processing all carried out right at the sensing front. And then the signal is being digitized into electrical pulses, and these are transmitted through the nerve to get to the brain. And also some pre-processing has taken place even before the signal get to the brain. And this is a very important information or scheme for us to learn to build electronics. That is, if we separate the sensing and signal processing at the upfront, then potentially we can have distributed sensors over very large area, and even have neuromorphic signal processing all built into the skin-like materials and systems. So when we ask that, well, silicon devices can already integrate all of these functions into such a small form factor, such as sensors, signal conditioning circuits, amplifiers, A to D, and signal processing, all in such a small form factor. It's indeed the case, but this means the sensing has to take place also in a very small region. And human body, consists of communication between electrical and chemical signal over the entire body. And we operate because the harmony of all of these signal be able to cooperatively interact with each other. And such a signal are generated from the cell level at tenths of micron, a few micron to tenths of micron, but communicate through the entire body at the scale of meter. So the electronics that we would like to interface with human ideally would also need to have cellular resolution in terms of sensing and mapping of information, but the signal needs to be collected over a very large area. And furthermore, the signal, if they are pre-processed, then this can allow significant reduction of power. So this is actually how it's done in the skin. That is, so these green dots represent the mechanoreceptors. They will respond to external shear force, vibration, or pressure, and the information will be combined at these nodes. Basically, these red dots are synaptic junctions, and signal are added at these junctions and generate a certain pattern that's being transmitted through the nerve to get to the brain. So if we can mimic such kind of signal, have sensor and the circuits, then these kinds of signal can also potentially be encoded into synaptic transistors. Then when there's a pattern of forces or texture of the object being sensed, it will generate a pattern that corresponds to that particular texture, and that will be remembered by the brain. Then this kind of signal processing can significantly reduce the power needed to process a large number of information, a large amount of information from many, many sensors. So this is another advantage of the biological system signal processing that, if we can incorporate into artificial skin, will be a key towards large-scale sensing electronics. So the ultimate devices that we envision basically will consist of circuits, sensors, displays, wireless systems, energy storage devices. So all of them will be based on materials that will need to have the form factor of human skin. So that has been the overarching goal for our research. And we believe organic materials and polymers in particular are very suitable for this endeavor, because organic materials are already known to have great intra-chain charge transport, charge carrier mobility for intra-chain, if can be actually leveraged in macroscopic devices, then the charge carrier mobility can even be on par with single crystalline silicon. The hopping between chains is currently limiting the charge carrier mobility to the level of amorphous silicon to polysilicon level. But still, the current best organic semiconductors and small molecule as well as polymer can already have charge carrier mobility as shaded in pink in the order similar as amorphous silicon and exceeding that of polysilicon, and on par with thin film carbon nanotube network and oxide transistors. And so that means they are already very promising in terms of their electronic properties for many potential practical applications. However, that's still not sufficient because we have to have sufficient advantages over the existing devices in order for a new technology to be accepted. But from fundamental point of view, to design the new generation of skin-like semiconducting materials and conducting materials possess a lot of challenges. That's because the molecular design for such materials, for electronically conductive or semiconducting materials, it requires the molecules to be rigid so that we can have the required energy levels and also good intra-chain and inter-chain pi-pi stacking. And this kind of structure leads to polycrystalline films that are also quite brittle. With less than 25% strain applied, large cracks can form in these kinds of films. On the other hand, if we want polymer films to be stretchable and highly flexible, then they need to have flexible polymer structures and conformation and amorphous film structures, but this usually leads to very low charge carrier mobility. So these properties or requirements for both properties seem to conflict to each other. So this becomes an interesting materials design problem. That is how we can have both properties incorporated into the same material and without degrading the electronic property. So our study on the fundamental aspects have been over the years to try to understand what in the molecular level are the mechanisms for the energy dissipation when we apply a strain to a thin film of polymer semiconductor or polymer conductor. And the basic mechanisms of molecular level events can be summarized here. Basically, the molecules can undergo rotation, chain elongation, chain alignment. The small crystallites can reorient, and to at some point, all the above mechanisms have been consumed, then the crystals will start to break, and eventually bonds will start to break. And when the bonds and crystals are broken, cracks may be formed in the film. And these processes are usually irreversible and lead to damage and degradation to the film and degradation to the electronic property. So our basic concept is trying to, from molecular design, to basically make the irreversible processes to be reversible and induce more of the other molecular level rearrangement into the materials system, but in a reversible way. So one quite successful concept that we have developed is to use partial conjugation incorporated into the otherwise very rigid polymer backbone. Here, incorporating 5 to 10% molar percent of non-conjugated unit can reduce the rigidity of the polymer backbone and lead to more amorphous thin film structure and introduce more disorder, which allows them to in the molecular level to rearrange. And in addition to that, if we incorporate these non-conjugated units as hydrogen bonding units, the weak hydrogen bonding allows additional possibility for energy dissipation under strain, but they can recover when the strain is removed. So this molecular design allowed us to realize the first generation of stretchable polymer semiconductors with charge carrier mobility on par with those of amorphous silicon for the first time. And our next generation was based on a more general concept where we realized that when choosing appropriate blending matrix, where the matrix incorporated the stretchability and the blending with the polymer semiconductor, and this can be almost any polymer semiconductor with high performance that's already being known. But of course, if you think about, usually you blend two insulator with a semiconductor or a conductor, normally you would expect the electronic property to be degraded because you're incorporating a lot of insulating material into the thin film. But to the contrary, we discovered several interesting phenomena here. One is by choosing the appropriate blending matrix, it actually induces the short range order or short range aggregation in the polymer system that actually give us increased mobility, even with adding 70% of the film consists of insulators, we still obtained an enhanced mobility. And by choosing the right surface energy between the conjugated polymer and the insulator, it will lead to a phase separation that still result in a continuous conduction pathway. But interestingly, this induced nanostructure formation can also decrease the glass transition temperature of the conjugated polymer, which has never been observed before. Even though it was known for traditional polymers such as polystyrene or PMMA, when you shrink the bulk material to more thin film, nanometer scale thin films, the dynamics of the polymer will increase. But this has never been observed with conjugated polymers before. And here we observe going to nanofiber compared to a thick film, neat film of the polymer semiconductor of 200 nanometers, the chain dynamics significantly increase, and the glass transition temperature can decrease by as much as 80 degrees C. And this can improve the ductility of the polymer in the nanostructure. And furthermore, the crystallinity of the film is decreased because of the confinement that prevents large crystal formation. So what we end up with is a stretchable film with much enhanced stretchability compared to neat film, but also at the same time, the charge carrier mobility, even with 70% of insulating material incorporated, is increased compared to the neat film by several times and reaching the charge carrier mobility of those of polysilicon. in the film. So that's quite remarkable, because that means then we have really been able to take the charge carrier mobility for the stretchable polymer semiconductor from originally, when we first started our investigation this area back in the 2010, the charge carrier mobility was orders of magnitude lower compared to the state of art. But now we added a new property into these semiconductors, but at the same time, charge carrier mobility did not decrease, but rather actually increase under even with strain. So this method is quite general. We can now use these nano confinement to add a number of new functionalities into the semiconducting materials or conducting materials with not only not compromising the electronic property, but actually with a boost. So for example, if we want biodegradability, we designed a matrix that matches the semiconductor that is biodegradable and stretchable at the same time. And the semiconductor, we have reported a concept a while ago that can make it degradable with weak acid by using these imine linkages for conjugation. So this can give us a fully biodegradable semiconductor. If we want self-healing to be added, then again, nanostructure formation is induced by adding a self-healing polymer with appropriate surface energy that's compatible with the semiconducting polymer. And this allows us to show for the first time that we can have autonomous self-healing of the semiconducting material without having to provide additional heat or solvent annealing. The semiconductor can recover the crack by itself at room temperature. So over the past number of years, through the fundamental understanding and developing various molecular design concepts, now we have a range of materials from conductors, semiconductors, substrate with added new functionalities, stretchable, self-healing, and biodegradable, but without compromising electronic property. So our current electronic devices, this is a thin film transistor, but our circuits and even coming up displays and diodes are all taking this new form factor of being fully stretchable and even can tolerate a very large strain or under very harsh condition, can still maintain the electrical performance without degrading. Now with the materials in hand, if we look at the history of silicon electronics development, it first started with a concept of transistors, and then it wasn't until silicon was discovered to be a suitable semiconducting material, and the growth of single crystal silicon was figured out. That was important materials development. And then the industry still didn't take off until integrated circuits was invented, and then eventually the photolithography method was really the enabling fabrication that allows the scaling of transistors and circuits to be able to follow Moore's law in the past 50 years. And the shrinking of the feature size allows the increased speed of transistors and circuits. So for stretchable electronics, we see that they have to follow the same lesson, basically learned from silicon devices. So with materials, then the next important development needed is to be able to fabricate not just one transistors, but rather many, many transistors, millions of transistors eventually reliably, so that we can actually build circuits and build useful electronics that can truly take the field to a new level. So that means each layer needs to be defined and interconnected to make such circuits. And this is both a challenge from material side, because the fabrication of the layers on top of each other will require materials to be and solvent to be compatible with each other, so the eventual realized circuit without degradation of the electronic property. And our guiding principle for the fabrication development is that we want to be able to fabricate each layer on top of each other without using any transfer process, because the transfer process may inevitably introduce some defects, even though it's possible to make a certain number of devices. But if we want to build circuits, we need extremely high yield for transistors. Just to give you an idea, if we have a yield of making transistors of 99% yield of the processing for making transistor arrays, then if we needed to make a circuit with 60 transistors, then the yield for the circuit would only be 50%. So we needed to have close to essentially 100% yield for the fabrication in order to build anything meaningful. So the process we developed is to first use a rigid substrate. This can be silicon or glass or rigid plastic. And we put a sacrificial layer that's water soluble. And then we developed the patterning method to pattern dielectric, semiconductor, and then the electrodes. And then we coat the elastic substrate on top. And then this whole thing passed through wood and the interconnect patterned. For the semiconducting layer, it was somewhat complicated because we needed to make sure the photo patterning doesn't degrade it. And we were using, we didn't have a photo patternable semiconductor at the time. So we first kind of put a protecting layer that's a fluorinated sacrificial layer. And this sacrificial layer on top, then we put a metal protection layer, and then we etch the semiconductor using the metal as the protecting mask. Then we remove the fluoropolymer and the metal to get patterned semiconductor with retaining of the semiconducting property. Inkjet, we also tested the inkjet printing. It can work, but the uniformity of the device was still not ideal. Then finally, for the electrodes, we use spray-coated carbon nanotubes and shadow mask. So in that case, the smallest channel length we were able to realize was 75 micron. And that limited the density of the device, so we were able to fabricate. Nevertheless, we were able to get to close to 350 transistors per centimeter square. And that allowed us to build this new generation of electronic skin that has 100 transistors and 100 sensors to map the shape of the ladybug. And also we were able to show for the first time that we can build stretchable circuits ranging from analog circuits to digital circuits and amplifiers and sensors. That's all built with stretchable materials and the process that we have developed. But as I mentioned, the first generation was still, the density was not, it was still modest. That's partly because the process still involves the traditional photolithography method that involve etching and the removal of photoresist. So since then, we have been developing a new process, basically converting all the active materials, the conductor, semiconductor, dielectric layer, all into directly photopatentable material. Then that means all we need to do is to coat each layer, photoexpose, and remove the unexposed region, and then coat the next layer and pattern. So it significantly reduces the number of steps and allows the yield for the processing to be much improved, and also allow us to produce high performance materials. But then that means we need to develop new materials again for this process, or new formulations, so that we can enable the photo patterning without degrading the electronic property. In the case of conductor, the spray-coated carbon nanotube previously was the limiting factor. So here we developed photo-patterned stretchable P-dot and maintain high conductivity. So here, the photo patterning was done through using these photosensitive methyl acrylate structure that can be polymerized upon light exposure. And then the high conductivity is maintained through using the this PEG structure. And the PEG will compete with the PSS in interacting with P-dot, and result in the aggregation of P-dot, actually give us a boost in the electrical conductivity. However, to photo pattern this film, we need to kind of choose the right formulation so that the boost in aggregation by the PEG is not too severe, so that the entire film becomes physically cross-linked and no longer photo-patternable. But we still need a sufficient amount of physical cross-linking and sufficient amount of cross-linker so that we're able to photo-pattern and have high conductivity. So that's what we were able to realize. And then this can give us a channel length as small as 2 micron instead of 75 micron in the previous generation. For the semiconducting material, we discovered that this diazyrine type of structure can be incorporated into a new type of crosslinker that we develop. And the diazyrine can react only with the CH groups on the LQ chain without damaging the semiconducting conjugated structure. So this can provide a mild cross-linking chemistry that's photo-initiated and allow us to obtain high charge carrier mobility photo-patterned stretchable semiconductor. And this is also used to pattern the dielectric layer. So compared to the first generation, now the second generation, we can have 42,000 transistors per centimeter square. So the density is much improved. These are the same scale actually for the images. You can see the transistor size are much reduced compared to the first generation. And the device shows a very good uniform charge carrier mobility that's on par with amorphous silicon and pretty narrow distribution. The circuits of the transistor can maintain the performance even after 1,000 cycles with very little change in the electrical performance. So this is the large scale fabrication, wafer scale fabrication, and then after release, these are the circuits that we're fabricating. So the one may ask why do we need such transistors to be such a high density? If we're going to high density, wouldn't that be competing with silicon? In fact, our vision is that these kinds of circuits are going to be mainly used for signal amplification and signal digitization. They are going to be placed right next to the sensors so that these signal conditioning are done right next to the sensors. And then the transmission of the signal to the final silicon chip can go through wires of certain distance without losing the signal. And this will allow us to be able to really distribute the sensors over a very large area, but still be able to have high quality signal and without having many rigid units all distributed on the body, but rather just have a central signal processing unit. So in that case, we also want the circuit to be rather small, and so that the each sensing unit can eventually maybe be at same order of cellular resolution. So with the current development, now we have transistor arrays of 42,000 per centimeter square realized. We're working towards the next generation of 100,000 transistors per centimeter square. We have realized 13.5 megahertz diodes. This is going to be coming out soon. This is very important for building wireless sensing platform. Stretchable polymer LED is also coming out very soon, and these are based on entirely stretchable polymer platform. So it will be a truly kind of stretchable display that we hope to realize. And stretchable PV, we already reported before, and lithium-ion battery also. We have demonstrated that there are a number of sensors in the passive wireless sensing tags. So each of the component entirely made of stretchable skin-like materials. They are being realized one by one. So now we're seeing really the possibility to start thinking about a fully integrated stretchable platform and the electronic platform being built in the very near future. Then I won't go into details in sensings, but there are also a number of sensors that can be realized with the stretchable platform. And the true advantage that I think these electronics that are built with intrinsically stretchable materials is that their potential matching with the biological systems in terms of preventing scar tissue formation, or even if the electronics can be made very thin, but the modulus could still impact the behavior of the cell differentiation. That's still something to be subject to study, but having compatible mechanical property potentially could allow cells to continue the differentiation and growth in similar environment as their natural environment. Other advantages could be for constantly dynamic changing size and the shape of biological systems. For example, morphing electronics is a new type of electronics that we reported recently, where this neurostimulator can continuously change its size and the shape as the nerve growth over time, and with exerting very small amount of force that caused no damage to the nerve. We implanted this into rat, small rat, baby rat, grow into adult rat, where the nerve diameter is increased, doubled, but we did not see any damage to the nerve with morphine electronics implanted. The other advantage for the conducting polymer, that is not just from the kind of mechanical property point of view, but rather really from the performance point of view. I think that's very important. That is when interfacing electronics with the biological system, they all have to, electrical signal have to go across from the electrode into the tissue. And in that case, the circuit can be modeled as a resistor and a capacitor that's in parallel. And for metal electrode, because it hardly has any capacitance at low frequency, then for metal electrode, the impedance at the contact with the biological system at low frequency can significantly increase for metal, especially for biosignal, for example, EEG, ECG, and EMG. They are all below kilohertz. In this range, the impedance for metal is extremely large. That can reduce the signal to noise for these kinds of electrodes. But the for conducting polymer, they can be designed to have a large capacitive term, and this capacitive term will significantly reduce the impedance. This can, what it means is that potentially using it for mapping electrical signal from human body, we can result in higher signal to noise ratio. Or with a small electrode, we can still gain similar level of signal compared to large electrodes for metal. So that means we can have higher resolution. And then when they are used for stimulation of nerve, lower stimulation voltage is required. So these are very important advantages that can allow the stretchable electronics to be able to realize cellular resolution, very small electrode size, and still maintain these stretchable form factor. Of course, using these rigid electronics with serpentine structure have already been demonstrated by Rogers and also Yonggang Huang. I think the advantage for conducting polymer is that one can start using really high resolution for these kinds of mapping purpose. Another area I think is a really very exciting new opportunity is the possibility to truly interface our electronic materials and systems with biological system in a very intimate way, and also being able to directly direct where the electronics can interface with the particular cells. This is a new concept that we just reported very recently. It's called genetically targeted chemical assembly. So here we envision that chemical structures, functional structures can be directly synthesized inside the biological system at specific locations we want. And this is in collaboration with my colleague Carl Desroff in the bioengineering department in Stanford. Here, the concept is to use genetic targeting to allow the attachment of oxidative enzyme to specific neuron cells. And this enzyme can trigger the polymerization of conducting polymer at only the regions where they are modified. And then in the control case, you will see conducting polymer, these black dots formed. And without the genetic targeted enzyme, no conducting polymer will form. And what's interesting is that we discover having conducting polymer can change the neuron firing pattern after these neurons are coated with conducting polymer compared to another related polymer but non-conductive. The firing pattern would be enhanced instead of being decreased. So this different firing pattern means that we can change the neuron behavior and potentially selectively excite certain neurons. So if you can imagine, if we have electrical signal that we want to selectively use to communicate with certain cell type, this could be a way to allow us to realize that. And currently we have demonstrated that this genetic targeted chemical assembly can be realized in cells, in brain slice, and also in live organisms to selectively deposit conducting polymer in these C. elegans, a small worm, and change its swimming pattern after we targeted the growth in certain inhibitory or versus excitatory neurons. So to summarize, our vision for the future artificial electronic skin is really a type of integrated skin-like system where these electronics not only take the form factor of human skin with new generation of electronic materials, but also with the fabrication methods that we have developed, then the signal processing similar to what our skin can do can also be realized in this system. So this can allow us to start building a really distributed sensing network over very large area. So we believe skin-like sensors and circuits and batteries are going to change our relationships between electronics and human, and also with each other. And this is going to be how we're going to interface with our surroundings, with our friends, and with our environment. And finally, I'd like to thank many collaborators, funding agencies, and many students over a number of years who have contributed to our vision and our journey. This was the time we were able to get together. Only recently we're getting together again, and it has been really exciting. Thanks again for having me at this forum, and I'm happy to answer any questions. Thank you.
谢谢包老师的精彩的分享。
Thank you, Professor Bao. Great talk. I'm sure there are many questions coming up. The first question is for PGDMA and PDOT. What is the interaction between PDGMA and the PDOT?
Usually stabilized by PSS. 否则 PDOT 它自己就不可以 dissolve in.
Otherwise, PDOT wouldn't dissolve.
Two functions. One is to help to dope the PDOT to make it conductive. The other is to surround PDOT with this negatively charged polymer so that the PDOT aggregate doesn't precipitate out. But having a lot of PSS will result in insulating polymer or very low conductivity. So the PEG is a polar polymer, it can kind of compete with PSS to interact with PDOT. Basically, it goes in and replaces the PSS. And then during this process, PDOT is able to be freed from the PSS and start to aggregate. And depending on the amount we put, if we put too much, actually the PDOT PSS solution will even form gel and cannot even be coated anymore. So we have to control the right amount, have small aggregates to increase the conductivity, but not so much so that it's already completely physically cross-linked.
OK，或者第二个问题是问的是说为什么要选择2种异晶双子单体？异晶双子单体。
异晶双子方体是什么意思？
单体是monomer。
异晶呢？
异晶是晶，我不知道这个或者怎么翻译。
对不起，我不太知道那个是什么意思。
我不知道听众里面能把这个英语单词打上。异晶双子是我查一下，看一下。它应该是我们先看下一个问题吧，包老师。他没有把这个英文单词打上来，我不太清楚。那么他下面问说这个晶体管在传感中会发挥什么作用
？OK， 晶体管的话是比如说我们的这边有一个这个 circuit， 像这边。
For example, here we have one circuit, and this is the temperature sensor. However, this temperature sensor in the silicon temperature sensor, they also use transistor, and the electrical is also electric dependence. And to use transistors into a circuit, if there is some external environmental change. Therefore, in this case, we have one sensor made by transistor. We can have a comparative circuit. So the signal output, the strain dependence, and all of them has been cancelled, so that the ultimate sensor is only sensitive to temperature.
Any strain or bending to the device. 所以的话，这些 circuit 是很重要的。
Therefore, all these circuits are very important. One is the circuit. You can have the sensors. On the other hand, the circuit and the sensor putting together. Usually, it sends the signal, especially EG, ECG, and very weak millivolt, maybe only microvolt. If electronics to sense, there should be an amplifier, and behind the electrode, there is an amplifier to amplify the signal to digitize it. However, if you want to do it, and there is one sensor, here is an amplifier. We are able to amplify the sensor. And then in the transition, and there is no intervention from the noise. So it is a sensor combined with the transistor for practical sensing system. This is very important. We need all of them. Professor Bao. Isoconic. Isocalinic. Sorry, I don't know about this English word. No problem. Let's move on. The other question is a very general question. The cost for the skin material, if used massively, what will be the core issues to be addressed? The cost is really up to the processing. By using photopatable material, depending on the feature size, if the feature size is only several micron or tens of micron, such a feature size could be large-scale produced. It's very straightforward. The cost is very low. In terms of the big challenge, first of all, these material and the processing are developed recently. Therefore, there are a lot of material and process problems.
Here 我只是 show 这个 demonstration of
Here,
concept.
I only show you the demonstration of the concept.
这个比如说 charge carrier mobility still only around 1 for fully patterned electronic circuit. We want to get it to between 5 to 10. Then we can start to build a circuit that's more in the hundreds of kilohertz 可能 megahertz 这样子的 range. 所以这个还是有一个很大的 gap. And then to fully realize commercialization, 它必须有这个可以 serve a large market, 有 large need. 所以这个哪一个 application 是 most suitable 的话，这个也是有点 chicken and egg problem, depends on what we can do, and then that means it can tell us what can enable. 我们现在还是在 very early stage, 只是
We are still in the early stage, only realizing, for example, transistor then transistor rays.
So we are going to display 像那些OLED 然后
OLED
那个 diode
wireless, step by step, all of them are built up. Then we can
out where is the place where this can play an important role, and while not competing with silicon, which is always a big challenge.
包老师还有最后一个问题是，可能是
One
来自
last question from the industry sector. He said, traditional circuit, and you have a welding. You need to have a welding material. But in the flexible electronics, and with the organic conductor or semiconductor, and how about the welding material between them?
这个确实是一个，就是说在我们即使做experiments 的时候，也是一个 very practical.
In our experiment, welding material is very practical issue. We have developed adhesive and which is conductive. And also anisotropic, which is also conductive. 那么
这个 material 它我们的那些 electrical contact with either flexible or stretchable 那个PCB and then connect to circuit board. 所以这个是还需要 further development. 但是existing 的 material 我们已经 have some material that fit the needs.
好的，好的，非常感谢包老师。
Thank you very much, Professor Bao.
谢谢您。
Thank you so much.
那我们下面是今天的
Next, we are going to have the third speaker,
那么是来自于美国西北大学的黄永华教授。
who is from
黄教授也是美国科学院院士。
Northwestern University Academician of National Academy of Science, of the National Academy of Engineering, Academician of American Academy of Arts and Science, Academician of European Academy of Science, Foreign Academician of the Chinese Academy of Science. Today, he is going to talk about modeling programmable drug delivery in bioelectron. Please go ahead.
谢谢这个Research Journal 的邀请。
Thank you, Research Journal, for the invitation. It's my great honor to have this opportunity to share with you our research direction, the recent progress. I try to translate it into the Chinese. It is called Modeling Programmable Drug Delivery in Bioelectronics with Electrochemical Actuation. I want to emphasize in the flexible electronics or the stretchable electronics, most of them are focusing on sensing. If we want to use it on human body, one of the major function, how to have the actuation, because you want to give the drug or medicine, you need more functions onto it. I want to share with you some of our practice. It is a joint work with John Rogers as well as my postgraduate student. Give you one example. The drug delivery system is divided into two. On the left hand is a systematic delivery. For example, you take pills, you have injection, or you have a patch. I need to have my mouse, the laser. Here you have pill, you have injection and patch, and all of which are the systemic delivery. The medicine goes into the whole body system, like your blood, different body parts, is the whole systemic delivery. The other one is the targeted delivery, which means you have a target, such as the nasal spray, and that is to spray into your nose. One is inhaler, something you can inhale. If you have blocked nose, it is a regional inhaler with no impact on the system. What's the difference between these two? Their functions are totally varied. For example, if it is cancer therapy, if you use systemic delivery, usually the therapy or the drug goes into the whole biosystem, a severe hurt to your body while killing the cancer cell. What we are looking for is a targeted delivery. For example, the cancer cell can be killed without influencing the whole body. Give you several examples in targeted drug delivery. One is the brain cancer. We can directly target at the brain and giving the medicine. The other one is skin cancer. There are some topical creams. However, by using the bioelectronics for targeted drug delivery, there is one problem there. In such a system, for example, the system given to a mouse to give injection into its brain by wearing such a big device, because the mouse is running around, and such a device should have a battery, and all of them have wires. It's not very convenient. Usually speaking, you can only give one medicine, one electricity, one light. Usually you cannot give several types of them. The other very great challenge, usually it is one-time application. The biggest problem is not very convenient. You need to wear it all the time. The mouse runs around. It's not very convenient to people. If you wear a big system on your back, it's very inconvenient. Great impact on your working life. You want something flexible electronics, which can go very well with the human body, but also it has actuation. For example, it's like a coin. It has two micro probe, and so that with a fluid which can give you the delivery. In 2019, John Rogers Group, together with our team, we developed a new type we can give a new delivery system. For example, it can be given to the body of the mouse. This is a flexible system and it is a wireless. And the power is wireless. You need no battery. All the signal transmission, such an antenna, are all wireless. You don't need to restrict the animal movement. You don't need to wear such a big box. I will give you more example. And it needs no battery. All kinds of things like the light stimulation and the drug can be combined and refillable after using up. However, one of the big challenge is to control the dosage and the time and the speed of injection.
I will first explain what is the process like. Here you have the mouse here in a cage. The cage is wrapped by antennas, and that is generating a magnetic field inside the cage. And in the brain, and there is a near field communication. And the strength of an NFC coil is you will be able to bring in energy through this coil, and when you need to pump drug, you would be able to automatically trigger that injection. So you still need to have an implantable, but energy and everything is transmitted wirelessly. It relies on the magnetic field to generate the electric flow, and then as a source of energy. But the activation mechanism is quite interesting. I have listed here a color-coded device. You have two chambers here. The one in pink is the one that contains a drug. The one in the bottom in blue is electrolyte. The reservoir colored in green is the surrounding area, and the orange one is substrate. Here at the top, you have a micro channel, and the purpose is to go through the micro channel to pump drug inside the human body. In the bottom, you have small electrolytes marked in yellow, and with a wireless transfer of energy and through electrolytes, you would be able to have reaction in the electrolyte chamber. It will generate bubbles, and purple colored line is a polymer membrane, a flexible membrane. Once you have bubbles in the bottom, then it will push up the membrane from bottom. So once you have current flow here, the reaction would generate hydrogen and oxygen, and then the extra bubble will push up the membrane and then push the extra drug into the micro channel, and then you would be able to have drug delivery. So the purpose of the study is to see how can we control this process as we want. So we need to address several questions. It's a complicated process. There are multiple parameters at play here. You have a solid membrane. It has to deform. You have liquids. You also have air bubbles here. Altogether, 12 parameters. To design control plans for 12 parameters, you would find yourself in a quite chaotic situation on how to control each of them. And also, material selection. You can use a PDMS or any other options. Each material is different. You need to calculate how each material deform. You'd need to have computers. You'd simulate. You'd need to run all the experiments necessary, and it can be quite a complicated journey. So what we are trying to do was to use modeling tools to help us understand how the 12 parameters change. So we will be able to narrow it down to 2 parameters. By controlling the 2 parameters, you'll be able to control the whole process. This is a major leap forward step for PMM or any other polymer material. You would be able to have a straightforward analytical solution that allows you to know the volume and the control rate. Then you don't need to rely on computer anymore. With a simple calculator, you will be able to get everything ready. That's the benefits of analytical module. Whichever material you use, how flexible, how rigid they are, you would be able to use a modeling process to calculate all the parameters. So I would like to first walk you through the 12 parameters to start with. Environment, because you wanted to pump it through, you would need to look at the pressure. For instance, P0 to represent atmospheric pressure. And then if it's within the heart, then the changing of pressure will also be represented here with pressure. And then within the microchannels, you would have 3 additional variants, A, B, and L, representing its height, its length, and also its 3-dimensional parameters. And the drug viscosity is another key area. Membrane geometry, you have 2 variants. And also the membrane materials, you would need parameters to reflect its core feature, including its modulus and how easy it will bend is reflected in these parameters. And you also need one for gas formation, another one for coil antenna. These 12 parameters jointly control the process, but we need to understand which is more important, which is decisive, how these 12 parameters interact with each other, or is it because of it, or they all work of equal importance, but by combining them into pairs or into groups, we'll be able to control them in much smaller numbers. So here, initially membrane was flat, but once it was pushed, you would have the form of the membrane into a spherical cap. Here, P represents the pressure coming from the reactive electrolytes with the extra bubbles. And then you also have pressure coming from a drug chamber. Then the difference between the 2 pressure has led to this deformation. And you would, on the other hand, have a volume of this spherical shape. The greater the pressure difference, the larger the volume will be. Then the function of F is obtained from this calculation, and it it correlates with the thickness of the membrane, of the Young modulus of the membrane, and also has something to do with the radius of the membrane. So let's say if the let's say it's a linear elasticity, which is impossible because almost all of the polymers would not be able to deliver that result. And then you would see how these different variants works within the function. But although this looks like a beautiful function, you would not be able to use it because when polymer materials deform almost exclusively, you don't have linear change. Then many would say we have to rely on computers, and you do the calculation and then read the results to see how it goes. This is a step that we did as well. But my point is, no matter how complicated the polymer material is, if you give me an we will be able to read the function through analysis, even if it's a nonlinear elastic change. And of course, if you don't have a formula to run your analysis, you still have to rely on computers. And another element to look at is the microchannel resistance. You have here pressure difference. The difference would give you a flow rate and the volume change as well. It's associated with the length, with the viscosity of the drug, with the key parameters of your section, cross section. Once you have both sets of parameters here, you'll be able to combine them and see the pressure is associated with your volume, with your very straightforward correlation with your fluid's properties. But it's still a complicated process because you need to understand where that pressure come from your electrolyte chamber. Where did that gas come from? It's based on the ideal gas law. It's associated with current. The larger the current, the larger the gas generation will be. F represents Faraday's constant, and it will help you to understand how fast the gas pops were generated. And under ideal gas law, PV equals NR/NTR, and you would see volume on the left side. You have it in moles, and then on the right side, you'll be able to get your results. And then you see it gives you the formula that associates the results with the time and the flow rate. But FV, I have highlighted here the variants that have an impact on FV. This looks like numerically quite straightforward formula with volume of the drug of time. And it's still quite complicated to find the solutions, because you would need to calculate FV out of the process numerically. And to start to resolve the calculus equation, you would need to use different numerical means to resolve it. You would be able to completely return to numerical means. I have marked here a computer. That means you would need traditionally rely on computers to study the changes of 12 parameters. But is it possible to use analytical means? I don't rely on numerical calculations anymore. Is there any way we can use perturbation method and membrane theories to turn a numerical solution process into a straightforward process that you'd only need a calculator to tell you the time. But this usually the doctor will tell you how many volume you would need, 11 millimeter, or how many and over how long a period, if it's 1 minute or over 1 hour. These two are key parameters in drug delivery. So we would need to pay attention to non-dimensional time, non-dimensional volume, and non-dimensional function. And once you have the formula, you would be able to translate it into a non-dimensional one.
And the T is the time for non-dimensional volume. And the V star and the T star, you need to get a solution. Very importantly are the two red highlighted letters. One is M star, that is the microfluid resistance, because you have the microfluid channel, you have the resistance. All the variables are put into combination, such as the dimension, the length, the thickness, as well as the temperature, the dimension of the membrane, and finally you have the parameter of M star. The other one is a P0 star, that is the air pressure or the environmental pressure. And finally, 12 variables into 2 variables by the non-dimensional. That is the microfluid resistance. The other one is initial environmental pressure. I only consider these two. No matter you are the electricity or the current or the temperature, and all of them are linear relation. Double curve, double temperature is the same. And also in the power of 4, you are able to change this factor. You don't need to consider these 12. You only consider these 2 variables instead of 12 variables. In order to solve this issue, first of all, M star, I suppose the M star is 0 without resistance. For example, it is a very large, and it is a very large section. If the resistance is negligible, we simplify the equation. This is the time. This is the current. This is the temperature. And this is the volume of the medicine. Here, this is very sophisticated, relevant to the ruggedness of your material. You need to calculate it by your computers, relevant to other external factors. Very simple formula. Even though you need to calculate by the computers, but immediately you can tell how much time you need. You turn very sophisticated issue into a simplified equation, even though you need assistance from the computer. And what are the factors? 8 instead of 12, because I suppose the solution without flow resistance M star is 0. That's why we have 8 parameters. And this is the final time you need. Here it is in the reverse relation to the current. Larger current, smaller time, higher temperature, less time, and a large volume, of course, longer time. Relevant to P0, higher pressure, longer time. And very nice equation. However, 2 deficiency, I neglect the resistance. Secondly, I need computer to give the solution. It's not good for the doctors to find out the result. And let's look at this one in this functional equation relevant to the membrane geometry and membrane material. In order to make improvement, I consider the resistance, which is not zero anymore. And in the past, we neglect the flow resistance, but now it is considered. This is an additional term, is obtained using the perturbation method. And with this perturbation, you get two things. First of all, and how much time you need for it. The purple one, because you have the channel, you have the flow, it goes through the channel, and the residue time to go through it and here. And this is without considering the flow resistance. But because of the distortion of the membrane and to offset the external pressure, and this is the flow resistance in the equation. Let's go back to, this is the current, temperature is here, the voltage is here, and the flow, thickness, section, and what is F here? F for nonlinear elastic. And generally speaking, relevant to dimension, to the length, you need to calculate by computer. I want to emphasize another important issue. I want to minimize the time by giving larger current. If you enlarge the current, it doesn't work. If you only enlarge the current, in order to overcome the distortion of the membrane, higher current, the smaller time. However, the section or the flow and how to add up the current without impact of it. And this is the real time and the joint collaboration. If you want to control, if you want to minimize your time, and you need to consider different factors. And I really want to talk about this with this formula. And I still give you the picture of computer. You still need assistance by it. Let's look at the numerical solution. And in comparison to the laboratory, to verify, to prove it, to verify it. Otherwise, I cannot give this to the doctors. For the electric engineer or computation or material science, and how to verify it. First of all, I have a volume temporal profile, the three curves coming from these formula. The red, the blue, the solid curve is my formula. How about the circles? By using numerical methods, and you can see the comparative result is quite good. And this is the maximum flow rate, is a relevant quantity in behavior. And this is very interesting comparison with experiment. Here, the circles, we use a numerical, and the line, the blue dots are the experiments, and this is the maximum flow rate. Here is the flow rate in comparison to the time, and the other one effective current. And they overlap with each other, and without any factors. And I just compare with the factor used in the lab. Based on the comparative result, we have confidence in the formula, but I'm not happy with it because when I show it to others, very important thing, like I mentioned, F1. Anyway, you need to calculate it. You need to calculate how this membrane is distorted. If FV by using it, and if F1 is also analytical, and all of the solutions are analytical, and everybody can use it. As with a calculator, you are able to do it. You don't need to know the distortion or the mechanism and or the rationality, you just need a calculator. You can find the answer. And let's analyze the dominated deformation here. And we want to look at FV, how the deformation is coming out. There are three types of deformation. First of all, it's a big edge. Big edge, that is the maximum deformation. It is called the biggest edge. If the biggest edge is small enough, which means a small deformation, and this is not applicable because in the reality, the edge is very large. What if it is small enough? You can have an analytical solution. Usually, we don't need to solve this electricity. And you are able to have an analytical solution. F1, here, this is the pressure as well as the volume. They are in the positive relation. And it looks very nice, but it doesn't work because the edge is large enough. And let's think about another situation. The deformation, the maximum deformation, far above small edge, the thickness of the membrane. It started with a flat, and later a semi-sphere, maybe it's larger than semi-sphere. It's also likely, interestingly, to give you the analytical solution. You don't need to do any, you don't need any assistance from computer. You just need a calculator. So the two extreme situation with the maximum edge and the smallest edge by analytical analysis with the calculator. Without computers, I got the results. And in the middle, it is highly complicated. Not large enough, not small enough. The deformation is similar to the times of the thickness of the membrane. You have to use the computer, but as the drug delivery, we want the details should be small enough. Just like you blow up a balloon and you need to give the delivery. And we can use this kind of analytical solution. But how to get the result? I will not go into details. I know that the audience, many of them, I know that you are not from the mechanical background. If the deformation is large enough, by using a membrane theory, which means at the beginning, the deformation is so large, and the balloon is blown up, it's a semi-sphere. The bending is not important. And later, it is not bended, it is stretchable. It is called membrane. And in all the deformation and the volume, there is the angle of deformation. And for example, parameters, and once it is changed, the volume can be displayed by the parameters. Deformation can also be displayed by it. At the beginning, it is a flat. And after that, you have this curve, radius, and the initial length, it is the stress. And then the strain in spherical cap, you are able to find out the pressure. Most important thing, your delta P is also the functional of the deformed angle. And this is, the volume is also a angle function. And they were read off by each other. And then you have a parameter equation. And what makes it so difficult? And in this pressure formula, there's one, it is called the true stress. You have a true stress. And it depends on the material model. If it's 30%, your force is more, but it is a low stress, you need a lot of them. Therefore, the true stress relevant to the material and all the others are geometrical. For example, the volume or the thickness, and all of them geometrical. Only this one is relevant to material. Just tell me what material you are, PDMA or PDMS or PDMA or other kinds of material. Just tell me what material you are. I can think of a way, and we can give you the information by analytical solution. And the other thing is a linear elastic, flexible membrane mechanics. And even though it is linear elastic, it has a large deformation. And this is the pressure and the angle. Once the parameters are read off and the stretching dominated deformation, and that is in the relevant to the volume in the power of 3. And with this, I can work out at the time for the analytical solution and the time for delivery. And how much confidence I have for it, I can make a comparison. And this is quite good overlapped. This is quite good. And the solid curve is analytical solution. This is the formula, and the dotted curve and is a very accurate numerical solution. And at the beginning, they are not very well matched. A little bit of gap here. Why? Because at the beginning, deformation is small, and the less delivery, deformation is small, but the bending is large. And therefore, in reality, when the membrane is large enough, no problem at all. The second, it is called flexible membrane mechanics, Mooney-Riveling, another very popular and utilization. And Mooney-Riveling by series of changes, and we are able to give you this analytical solution.
And here you would see how the dots represent the analytical results, and it perfectly align with the actual observation. But for the real world material could be very complicated. For instance, we have one type of polymer called SBS. You would need to understand how SPS performs. You need to calculate its stress and strain curve so that you would know how rigid this material is. Once you have the stress strain curve, it would be sufficient enough. It's called a Marlowe model. I don't make assumptions. Marlowe model is based on the stress strain curve. It's completely based on the curve on the right side. So once you have a Marlowe model, you would be able to perfectly fit with your curve, because you don't need coupling. It's completely based on the stress strain curve. So you give me a material, we would need to have the stretch curve here. Once it's available, you will be able to fully calculate the result here. Although it looks like a complicated formula, but actually with the curve, you would be able to analytically run everything. You again see the calculated the calculated results represented in dots perfectly aligned. Although it looks like the same formula as we had, but you no longer need a computer anymore. With calculate, you will be able to calculate everything. As long as you give me your strain and stress curve, you will get everything. Here, you would need you would know the time of the curve of the deformed membrane, and you would know the flow rate change. With this, you could do anything you want with this model. Here, the yellow blocks are numerical models, and on the right side, you have analytical results. It's quite well aligned, because usually you start with a fairly small M star. And with this at hand, it becomes very useful. You could give it to electric engineers and those who make device to play with. For instance, another example is SBS. it has different curve. And once again, you give me your curve, I will be able to calculate. You would see on orange is marked for SBS and SIS, again, with its parameters. It's quite useful because once you know the material, you would be able to tell how long you would need for the drug delivery. I'd like to talk about a quite interesting application. In US, right now, it's struggling with opiate. I carefully looked for its Chinese translation. Opiate is becoming an epidemic in 2019 alone because of the use of opiate. Reported deaths were close to 50,000, and the trend is coming up. Even in the context of COVID-19, as of this June, total death toll was 500,000. So to put the opiate reduced deaths in the context of COVID-19, it's already 10%. And remember, I was only talking about annual death rate incurred by opiate. So opiate is a real threat. So is it possible to implant a device in human body that can not only monitor different biological parameters such as blood pressure, your oxygen content in your bloodstream, your body temperature? For instance, if you detect the lack of oxygen, there might be signs for drug use, and it would automatically actuate the drug to save the drug addict when necessary. For instance, our experiment was initially done on mouse, and it's a different story for human, because for mouse, it's only at the you only use a minimum amount, but for human you would need 120, and the radius would also be significantly larger, 5 millimeter versus the 1.2 millimeter in mouse model. And we have young modulus, and the curve here represented here. The temperature is a mimic of the body temperature. Once you have all the parameters listed here, you would be able to use these straightforward formula to calculate what would be the delivery time. If it's 1 hour, then it's the drug user would be long gone. 1 hour is too long. We could calculate and compare across different materials. For instance, if it's SIS, the modular, the more is 5 ampa, and if it's SBS, then 95 seconds. But if you just for comparison purpose use a linear elastic material, you would need around 3 minutes. Because compared with linear elastic material, the two polymers indicated in the top are more flexible, and they could allow the movement easier. And this could be useful for those who work on devices because they will be able to design an electro and chemical actuated changes. And to sum up, the start of the journey may seem overwhelming for anyone because 12 parameters, you have gas, you have pressure and everything. But upon the analytical approach, you'll be able to narrow it down to 2 parameters. And even better, you don't need to rely on computers. With a simple calculator, you'll be able to calculate volume and flow rate. Flow rate is another key parameter. I don't have time to go into that, but it could be detrimental to human body if it's too high. So anyone with basic secondary school education will be able to calculate the result. Thank you, Professor Huang. Now it's time for Q&A. We have a question here concerning the size of your device. How small can it be? On organisms, on human body, how small it can be? In practice, in mouse model, it's a several millimeter. It's already very nice. And then what about weight? It's still it's ultra light, but you have to take into account the weight of the medicine. But it's ultra light. You don't need a battery because the energy is transmitted wirelessly. It's controlled wirelessly. You don't need a battery. Once you put it within a certain range, you don't need to constrain the movement of a mouse anymore. So what do you see as challenges if we were to use it on human? Many. For instance, well, so these challenges are not within the design of our device itself. The challenges lies with medicinal application, for instance, which is the target region. How do you would you properly implant it to the target region? So on device side, how do you activate the device is almost close to perfect. So on the design side, the challenges is not with how we design, but rather how we respond to medical needs. So this is not something we can do within our own team. We will have to work collaboratively with doctors. No further questions for now. Thank you. Thank you, Professor. I'd like to once again thank all three experts for the morning session. If I may, I noticed Mr. Cui raised hands. I have a question for Professor Huang.
Great. It's great to see the recent progress.
谢谢，我想就是插一句哈，这个
If I may jump in here, we quite enjoy our cooperation with Zhang Hassan, because whenever we prepare a model, they wouldn't request us to apply it to a complicated system. And he would artificially build a straightforward model in vitro in our environment. You would be more comfortable of applying your process step by step. And for each parameter, we'll be able to test it in separate models, and then you integrate it into one combined process. We are not required to work on a complicated scenario in vitro setting. Sorry for interrupting you. I have a question here for you. You have done a nice model with Roger, but you are working based on an ideal membrane deforming process. But if the polymer materials is non-homogeneous,
reason, then how can we do with it?
我想说一下，就是如果你真正签到就是如果说你材料的复杂性
If the material, I'm not afraid of material complexity anymore. Linear, non-linear material alike. As long as you give me your strain stress curve, I will be able to analytically tell the time. So it is included in your FV, right? Any material long linearity can be included in FV, and it's analytical. You would only need a calculator. If you would artificially design the membrane into a structure that is not uniform for whatever reason, it's also okay. You design it, and then it's almost like trying to blow an air balloon. If it's uniform, then you have a perfect ball. But if it's not uniform, it wouldn't be of the perfect circle or round shape. But still, you'll be able to run analytics here.
Because the thickness is different and the stress distribution is not even. As long as the thickness, even though thickness is not evenly distributed still, and I can still give you an analytic solution of FV without using computer, unless it is so complicated by human factors. You use several materials, and maybe it is more complicated. The membrane, you use a lot of material, but it's fine. But you have to use computer to give the value of FV. The equation still works. Thank you. Thank you very much, Professor Yonggang. Academician Mr. Huang, you have a question? Yes. I think that all the presentations today are very exciting. The presentation and the report made today and really make us know more about flexible electronics and its future application and the skin-inspired electronics. I believe all these research work are very expected, are hopeful for the Nobel Prize. And Professor Zhong Nan, and I think that your work is capable enough to be nominated for Nobel Prize. And yours is a theoretical innovation. And Professor Yonggang's presentation, I try to think about this question. And Lu Chun, and we have done a lot of modeling simulation work and chemical training together with academician Chongnan. When we were in Peking University, we learned a lot of math and numerical analysis, a lot of work. However, when we review our work and time spent on it to deal with such a sophisticated modeling, to find out the 12 variables and such kind of equation or such a system, to us is almost impossible. And to simplify it into 2 factors, and this is a very good way of thinking, providing good foundation for the flexible electronics in constructing the liquid mechanics, theoretical framework. And all these are very insightful, inspiring, because a lot of non-dimensional factors in the fluid mechanics. Maybe we can also have take your name as a Yonggang number. And altogether, we try to apply the models to other scenarios to construct a theoretical framework for the flexible electronics, very critical for the development of such a subject. Academician Mr. Yonggang, yours is based on silicon material. Zhongnan academician, our team, is built upon the organic material, Jianpu and Yonghua. and their research work is built upon the organic and inorganic, the perovskite material. And finally, we move towards the flexible application. Still, we still have some commonality. And in a results based on the large experiment, probably we can find more similarities or commonalities between that. And this needs a mathematician like Professor Yonggang. You need to have very solid foundation for it. And your work is such a great one. And we show our respect, and we want to enhance our work and to promote the development of the flexible electronics. I really want to thank the two academicians and Professor Yonghua for your wonderful reports, and I feel I learned a lot from you. Thank you. Take care. Thank you very much. And Professor Huang, and that's the end of today's forum. Thank you all of our experts. And I look forward to Professor Zhe Nan, Professor Yonggang to win Nobel Prize and international prize. And just like organic electronics 2000, Makadame Shirakawa win the Nobel Prize, which is a very good consensus or the acknowledgement to the organic electronics. That's why 5 or 6 years later, companies like Samsung have such a great progress, especially in OLED. And in the recent 15 years, such a large, massive application in the market, great contribution to the humanity and flexible electronics. And I do hope that you can take the lead and to start waves of research to make it fully commercialized. Thank you very much. Thank you. Thank you, Professor Huang, and it's my sincere hope for the future. Okay. Yes, a lot of hope there. Thank you, Professor Huang. Bye-bye. Professor Bo, bye-bye. That's the end of today's forum. Thank you, bye-bye. Thank you, everyone. Thank you. Congratulations to your report. Very good one. Very good one. Thank you. And we leave some time for the audience. Okay, thank you. Bye-bye. Hope that we can have an offline meeting very soon. Okay, thank you. Bye-bye.
好，谢谢天虹，谢谢永超。